Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on the binomial distribution. So this is like an extension lesson because you might find using this formula I'm going to give you much easier than using tree diagrams. You can use the binomial distribution in place of a tree diagram when the question is a with replacement question. So let's look at the kind of question for which we could use the binomial distribution. So let's say I roll a die 4 times. What's the probability I roll exactly 2 6s? Now we could draw a tree diagram. So of course we wouldn't go 1, 2, 3, 4, 5, 6. That would take forever. There'd be way too many branches. Instead, we could draw a tree diagram that has 6 or not 6. 6, not 6, and so on. But because I'm rolling the die 4 times, there will actually be 16 branches. This will take a while to draw. So instead, let's look at this another way. So I want to know the probability I get 2 6s and 2 things that are not 6s. So let's find the probability, for example, that if I roll a die 4 times, I get a 6, then a 6, then not a 6, and not a 6. So, of course, each time I roll the die is independent of the previous time. So I can just multiply the probabilities. Probability I get 6 on the first go is 1 over 6. The probability I get 6 on the next go is 1 over 6. The probability I get a not 6 on the third go is 5 over 6, and then same for the last one. So as I said, because they're independent, I can just multiply these together. So really, this is just 1/6 squared times 5/6 squared, right? That's the probability that this happens. But see, the reason that we went through tree diagrams, and the thing that's a little complicated, is that I can get exactly 2 6s more than one way. So this is one way I could get 2 6s. 6, 6, and then 2 numbers that are not a 6. But of course, I could also have got a 6, then not a 6, not a 6, and then a 6. That would have exactly the same probability here. It would be 1/6 squared times 5/6 squared. So the 1/6 squared comes from the 2 6s. Probability of this is 1/6. 1/6 times them together, you get 1/6 squared. The 5/6 squared comes from the 2 not 6s. This has probability 5, 6. This has probability 5, 6. Probability they both happen, I just square them, right? But there's more ways that this could happen, Another way it could happen, I could get a 6, then not a 6, then a 6, then not a 6. And it would have exactly the same probability. So remember, what I am essentially doing when I use a tree diagram is I'm finding all of these possibilities, all of the ways that I could get 2 6s and 2 not 6s, and then I add them all up. So when I had figured out all of the ways I could get exactly 2 6s, I would just be adding this up over and over again. This number, 1/6 squared times 5/6 squared, which is like 25 over 1,296. But of course, there's a quick way to do it. So how many different ways are there like this? How many different ways could I roll exactly 2 6s if I roll the die 4 times? So think of the positions. Position 1, first roll, second roll, third roll, fourth roll. There are 4 different positions or 4 different rolls. 2 of those have a 6 and 2 don't. So the total number of ways that I could roll exactly 2 6s is just 4C2. 4 rolls, and I'm picking 2 of them where I rolled my 6s. So, of course, 4C2, you can use your calculator, or Pascal's triangle is just 6. There are actually 6 ways I could get this. So, the probability that I would roll exactly 2 6s, well, each of these 6 outcomes, these ones I'm talking here, has probability a 6 squared times 5/6 squared. So I'm adding up this number 6 times. And of course, the easy way to add it up 6 times is just to times it by 6. That's what the probability would be. So it turns out the probability would be 25 over 216. That's what you get if you put that on your calculator. So what if I didn't want to know the probability I roll exactly 2 6s? What if it was another number, like I roll 1 6 or whatever? So this is the idea of what we've done. So let's say I roll the die 4 times and the number of 6s I get is x. So what the probability would be that I get exactly x 6s, it would be 1 over 6 to the power of x. So 1 over 6 is the number of 6s I get to the power of 6. So for 2 6s, it was 1 over 6 to the power of a half. For 3 6s, it would be 1 over 6 to the power of 3. And then what I'm going to do is times 5 over 6 by the number of rolls I get that are not a 6. So that's 4 minus whatever x is. And so I times that by the number of ways it could occur. So this is how I would figure it out really quickly for if I rolled a die 4 times and I wanted to know the probability I get, like 1 6 or 3 6s or whatever. I could just substitute into this formula however many 6s I want for x. So this is how we get the formula for the binomial distribution, which I'll now write on the next slide. So this is the formula for the binomial distribution. So n is the number of trials you perform, like the number of times you toss a coin or roll a die or whatever. X is the number of times you want something to happen. P is the probability that it happens each go. And of course, 1 minus P is just 1 minus that probability. So let's say I toss a coin 10 times. What's the probability I get exactly 5 heads? So this is a with replacement experiment because the probability of getting heads each time is the same. It's a half each time. It's like if you get a head the first go, it's like it's replaced. You can get a head the second go. So we can just use this formula up here. Now we could draw a tree diagram, but if we were to draw a tree diagram, the number of branches would be 2 to the power of 10, which is 1,024. Drawing a tree diagram would take forever. Instead, we use this formula. So here, n, the number of times I'm tossing the coin is 10. I'm interested in getting 5 heads, and the probability I get a head each time is a half. So the probability I get exactly 5 heads is 10c5 ncx times p to the power of x times 1 minus p. Now 1 minus a half is a half times a half to the power of 5. And if you put that on your calculator, you get 0.246. So that's the issue. This formula is complicated to understand and to know what's going on. But if you do understand it, this is so much simpler than drawing a tree diagram. Let's look at one more example. So let's look at this question here. Normal 52 card deck. Take a card, put it back, shuffle the deck. We do this 8 times. So basically we're picking 8 cards from the deck with replacement because I put it back. So what's the probability I pick exactly 3 hearts? Well, here the number of times I'm picking a card is 8. I'm interested in getting exactly 3 hearts. Each time I pick a card, the probability of getting a heart is a quarter. So the probability I get exactly 3 hearts is ncx times p to the power of x times 1 minus p. So 1 minus a quarter is 3 quarters to the power of 5. So this is saying I get 3 hearts. That's the probability I get 3 hearts. This is the probability I get 5 not hearts because the probability of not picking heart is 3 quarters. And this here, remember, tells us how many ways we can get it. You know, we could get a heart the first 3 goes and then 5 not hearts. Or we could get a heart, then not a heart, then 2 hearts, and then 4 not hearts, and so on. This tells us how many ways that can occur. So we can just put this straight on our calculator. So putting that on our calculator, we get about 0.21. Once again, so much quicker than if we were to draw a tree diagram. It would have too many branches. It would take forever. This way is a lot simpler, just a bit harder to understand. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.